All right, let's get started. So thank you for coming to my talk, and I'm very happy to give a talk in the potential theory in probability theory. So my name is Hyunchul Park, and I work for SUNY Newport, New York, United States. And today I'm going to talk about spectral heat content for time-changed killed Brownian motions. So this talk is based on joint work with Kei Kobayashi, who's working for Fordham University. And our work is submitted and it is available in the archive. All right, so this is an outline of my talk. So I'm going to introduce the main problem, what we want to study in this talk. And there are two main results. This is about the asymptotic behavior of the spectral heat contents when time is small. And the spectral heat content is given by time-changed Brownian motions, and where the time change is first, time change is given by a large class of subordinators, which is an increasing Levy process. And second case is the time change is given by inverse subordinators. And then at last, I'm going to introduce some open problems that I am interested in. All right, so here's the introduction. So let me introduce spectral heat content. And this is a very natural object in analysis and probability. So we consider a basic heat equation with a Dirichlet boundary condition. So I'm going to denote this VD/Bm to be a temperature of the domain. So we have a domain D, and over here, the temperature, initial temperature is 1, and outside the temperature is fixed to be 0. And then the time start to diffuse. The heat start to diffuse, and then heat decays. And then we are interested in what's the temperature, how the temperature changes. Okay. So this V function is a temperature, and then we put the Bm for Brownian motions because this heat equation is closely related to Brownian motions. And this temperature function, which is a solution of this basic PDE, is also given by in terms of a probability. And the probabilistic representation is that this temperature function is given by the survival probability of a Brownian motion. That is, if we observe the Brownian particle over here started at x, and the temperature function is given by this particle does not exit the domain by time t. That's given the probability that the exit does not happen until time t. And this is also given by some integral of a heat kernel. So this object is closely related to analysis, PDE, and the probability. And then the spectral heat contents measures the total heat at time t. Because of a Dirichlet boundary condition, the heat start to decay, and we are interested how fast or how slow this heat decays. So this Qm QdT for Brownian motion is just the integral of all the temperature. Okay, so this is a spectral heat content for Brownian motions. And what we are interested in is we are interested in non-local spectral heat contents or spectral heat contents with respect to jump processes or Levy processes other than Brownian motions. So the setting is exactly the same, except that we replace this Laplacian, which is an infinitesimal generator of Levy processes, by infinitesimal generator of any Levy processes. In this case, infinitesimal generator of time-changed Brownian motions. And we also need to slightly change the Dirichlet boundary condition by Dirichlet exterior boundary condition, because in this case, the heat particle can jump strictly outside exterior of the domain, not just the boundary, but it's a jump process. So because of this, we need to have an exterior boundary condition instead of a Dirichlet boundary condition. Okay, so subordinate Brownian motions is a very special case of jump processes. This is a time-changed Brownian motions. So if we have Brownian motions like this, then we observe the Brownian particles at the independent time, where the time is given by ST, which is the subordinators or increasing Levy process. So it's another time. It's a random time, and we observe this Brownian motion by it's a random time, and this becomes jump processes because of the time is a random. And what is good about this subordinate Brownian motion is that this consists of a large class of Levy processes, but this is still more tractable than general Levy processes. Maybe more a general Levy process is difficult to study, but subordinate Brownian motion is more tractable, and it includes a large class of interesting examples. Okay. When we study the spectral heat content for jump processes, especially spectral heat content for time-changed Brownian motion, that we need to do two operations. We need to do time change, and we need to do the killing, or we need the killing. The particle get outside of the domain, then it's killed. So depending on whether we do the time change first or killing first, there are two kinds of different spectral heat contents. So the first kind is that we first do a time change first, and then observe them until they exit the domain. So this is called the spectral, the killed subordinate Brownian motions. Because we do the time change first and the killing later, or we can switch to this operation. We kill the Brownian motion first and then apply the time change, and this is called subordinate killed Brownian motion, because we do killing first. These two objects are closely related, and in this talk we'll be interested in this object, the subordinate killed Brownian motion or time change killed Brownian motions. So these are two spectral heat content for killed subordinate Brownian motion and subordinate killed Brownian motion. And this second object is something that we'll be interested in this talk. And there is a close relationship between these two. So one reason why this is interesting to study is that this object, which is a killing of the subordinate killed Brownian motion, is contained in this set, which is the lifetime of killed subordinate Brownian motions. It's because the particle can go outside and then come back, and when the particle is not observed when this make the excursion outside the domain, then the subordinate killed subordinate Brownian motion, when we observe the time change process, then time change process is not observed when the process exits the domain. So this process only has to be observed at the random time change, so that there is a slight difference between these two processes. So that is, this object provide a natural lower bound for this object. So we can take advantage of one object. So if we know the information about one object, then we can make use of the information. We can extract some information for the other object. So this is one reason why we are interested in such object. Okay, so here's the main questions. The main question is, can one find an asymptotic behavior of the spectral heat content for subordinate or time change killed Brownian motions when the time change is given by a large class of subordinators or inverse subordinators, inverse subordinators. And here are main results. There are 4 results, and it depends on the main assumption. One of the crucial assumptions is that the Laplace exponent of the subordinator is a regularly varying of a certain positive index. So we assume that Laplace exponent of subordinator is P lambda. The P lambda is belong to regularly varying, where beta has to be between 0 and 1. Beta is strictly between 0 and 1. And for subordinate case, then there are 3 cases. Beta is between 1.5 to 1. The beta is exactly 1/2. And the beta is between 1 and 0 to 1/2. And there are 3 different regions. And in these different regions, that asymptotic behavior of the spectral heat content for subordinate killed Brownian motions are different. So first case, when the phi is a regularly varying with this index, then this is a right order of the decay, and then this is the exact coefficient is given by this term. And the one where this S1 is a stable subordinators. So one interesting feature of this result is that this limit does not depend on anything other than the index of regularly varying. So this right-hand side only depends on the value of beta, but it does not depend on other things. So when beta is a 1/2, the picture is not complete yet, and we could prove that a special form that the Laplace exponent is this term, this main term, plus lower order term perturbation. Lower order term perturbation means that this remainder is regularly varying with less than 1/2 regularly varying index. Okay, so this is when beta is 1/2. And finally, when beta is low, then the decay rate is given by t, and the limit is given by this form. So these 3 results are for the asymptotic behavior of the spectral heat content for subordinate killed Brownian motions, where time change is given by subordinators. And this is for result for the inverse subordinators. So we observe the time change Brownian motion where time change is given by this inverse subordinators. Then this is the asymptotic behavior of the spectral heat content by inverse subordinators. In particular, in this case, when the time change is given by inverse of a stable subordinators, so then we could prove the pooled asymptotic expansions. And this is, as far as I know, that this is the first such a result for complete asymptotic expansion of the spectral heat contents for non-local processes. Okay, so the time I'll finish in one open question. So all the results so far is about the spectral heat content for killed subordinate Brownian motions. And it's an interesting question to ask about what happens for subordinate killed Brownian motions. So killed subordinate Brownian motion. So we have one information about the one object, and we are interested in information for the other object. And because we know information about this object, then this gives a natural low bound for this guy, and we are interested in the spectral heat content for killed subordinate Brownian motions. Okay, this is the reference, and thank you for your attention.